because we'll have our exam on Monday, and it will be in this room at 7:15. Listen, I really want this exam to be a boost to your grade before we go into the final. So I'm not saying it's easier, but if you stick to the homework, you should be okay. And then look over the concept test for chapters 5 and 6. I'm going to have fewer multiple choice on this one, probably 5 to 7 instead of 15 like I usually have. And so they'll be worth less. So really stick to the homework. Y'all clear what I'm saying? They're not going to be just like the homework, but they'll be similar. Also look at the examples that we did in class. They're similar to the homework. So as you're studying this weekend, you want to focus on the examples and then look at the homework as well. As I said last time, you're not going to see anything from the latter half of chapter 7. So stuff about phasors, stuff about driven oscillators. If it says AC circuits in it, then you're not going to see it. I think I pointed out to you in the homework which ones to leave off. I did point out to you the ones in the homework to leave off, as well as the ones in the old exams to leave off, at least from last semester. All right, let me just sort of step through where we're going. So you're going to see, picking up on page 158 in your notes, where we have the magnetic force on a current-carrying conductor. You can see that. You might see a cross product. There's some homework questions about the cross product there, though we did cross products before, so I'm sort of uncertain right now whether we'll see cross products again. But you need to know how to find the magnetic force on a current-carrying conductor. And then also, don't forget your right-hand rule. So if you want, after I sort of give the summary of what's on the test, we can go over the right-hand rule and the different applications. Look at your concept test for good practice in that, because your multiple choice will probably cover much of the right-hand rule stuff. All right, just some examples of problems that we had. You can see the torque on a current loop. This comes up with our motors and our generators, the amount of torque that they give. Largely, this is just knowing the equation sheet and knowing how to apply the equation that we have, because we can calculate the torque, and this is given to you on the equation sheet. This number of coils of wire times the current times the magnetic field times the area. Remember that applies whether it's a rectangular loop or a circular loop or whatever type of loop it is. It's the area of that loop. So pi r squared if it's circular, side times side if it's rectangular. Example we had. I need to know how electric motors and electric generators work. All right, so, and then also the mass spectrometer. We did a problem like this in class where we determined the unknown particle. You're almost certainly going to have a mass spec on the test, because y'all use mass spectrometers, and I want you to know, the basic underpinnings of how the mass spectrometer works. So you can almost certainly guarantee that you'll have a mass spectrometer. Where I give you a particle that's traveling through a magnetic field, and I could ask you various things like, what is the radius of the path? Or I give you the radius of the path, and you have to figure out the mass to charge ratio. So nothing terribly deviant from what we did in class, but I just want you to know how that mass spectrometer works. I might also ask you to describe in words how it works, a sentence or two. So y'all use mass spectrometers, so it's important to know. Magnetic field of a long straight wire, know how to calculate. Be careful on your equation sheet, because we have a couple of different equations that look very similar. We have this one for the magnetic field of a long straight wire, and then we also have this one for the magnetic field of a coil of wire. Notice that this coil looks very similar to the other one, which was mu naught I over 2 pi r. But notice the difference in the two. This is for the coil of wire, the magnetic field in the middle of the coil of wire, and it has the number of loops of wire. And so that's how you can distinguish it, that it has this N in it, and it's missing the pi. But the N always sort of keys me off, because if I'm looking at the magnetic field of a long straight wire, I'm almost always just looking at a single wire. You're not going to see you're not going to see this, the magnetic force between two parallel conductors. I think there was a homework problem in that, but you won't see it on the exam. Okay, so we had mass spectrometer, the force on a current carrying wire and a magnetic field. We had various right-hand rules. We'll go over that. I'll summarize that for you in just a minute. Get everything here. A torque on a current loop, that's like in an electric motor or an electric generator. Mass spectrometer, magnetic field of a long straight wire. Not magnetic field between, magnetic force between two parallel conductors and solenoids. And that'll be it for chapter 5. All right? You all with me so far? You want to go over the right-hand rule quickly? All right, let me show you. There are a couple different applications. I'll just do this on 171. We're not going to see one like this where I have a particle moving through a magnetic field like this, but it works much the same way as the wire moving through a magnetic field. So let's just take a look. So here we let our index finger go in the direction of V. We let our middle finger go in the direction of B, and then our thumb gives the direction of the force. So index finger, middle finger is into the page, and so this particle will feel a force that's upwards. So the force here is up. B is to the right. My middle finger could go in any direction, with B being to the right, but it goes into the page because the magnetic field is into the page, and then my force is going to be up. That's important for the mass spectrometer too, okay? So you could see some questions where you have to still apply this. But it's also true for the current carrying wire. So if I just replace that free charge with a current carrying wire, I, it would be exactly the same. B, I would let my index finger go in the direction of I, middle finger in the direction of B, and then the force on this wire would be up, and that would be your thumb. So it's identical to that. Now, there's a third application, and often I like to combine these. So there's a third application, whereas if I have a current carrying wire with a current in that direction, it generates a magnetic field because, you know, magnetic fields are caused by moving charges, and I have moving charges moving through this wire. I let my thumb go in the direction of the current, and then my fingers wrap around to give the magnetic field. So it looks like this. My fingers go into the page on this side, out of the page on that side. So my magnetic field around this thing will look like this. We had some problems in the concept test, which is online. It's on the website, where, for example, we had two wires, say two wires that look like this, and I ask you what is the net magnetic field, say at this point P, and you would do something like this where you'd find out what is the magnetic field surrounding each wire. It's going to look around this wire right here, thumb into the page, it's going to go clockwise like that. So at point P, my magnetic field is going to look like that, tangent to that circular magnetic field. Due to this wire, it's also going to go clockwise like that, and so at this point my magnetic field looks like that. So my net magnetic field is going to be to that side. So you'll have multiple choice questions. They'll be a lot like what you see on the concept test. Make sure you can get through them. I would print them out, 6 slides to a page, fold them in half, and then you can sort of quiz yourself on them. Okay? So your right-hand rule stuff will largely be in the multiple choice. So it might come up in things like doing your cross product, or maybe with the mass spectrometer figuring out the sign of the charge, because the sign of the charge says whether the charge goes up or whether the charge goes down in a certain magnetic field. Remember, if you have a negative charge, you just switch the direction. Stick to the homework. Look at the homework carefully. Make sure you know the mass spectrometer, and to go through the examples in the notes as well, but you'll certainly have a mass spectrometer. Okie dokie? You okay with chapter 5? As I said, I want this to be a good exam grade-wise, so we get a little boost going into the final. But I mean, it's not going to be easy. If you don't know how to do the homework and the concept test, then you won't do well, probably. But make sure you can do the homework, and you'll be good to go. You understand what I'm saying? Okay. Let's look at Chapter 6. All right, Chapter 6. So you're going to need to know Faraday's Law about how a magnetic field, a changing magnetic field, can induce an electric field and can induce then a current. We worked through some problems where we found that changing magnetic field. You can see some conceptual things here, like where we had the graph, and we had to know what was the electric field that was induced, the EMF that's induced, based on the changing magnetic field. So if you remember this, we had a starkly changing magnetic field here, and so that's our biggest EMF, our biggest induced EMF, our biggest electric field that's induced. This is the next biggest change in magnetic field, so that's the next biggest EMF. And in these two cases, the magnetic field is not changing at all, so there is no EMF induced at all. So in order to have an induced EMF given by this Faraday's Law, this dP dt, N times dP dt, you have to have a changing magnetic field. Not just a magnetic field, but it has to be a changing magnetic field. We talked about ways we can do that. We can change the magnitude of the magnetic field, or we can change the direction of the magnetic field. The latter is more common in generators because it's easy to spin that coil of wire to change the direction of the magnetic field as it interacts with the wires. Let's see, we did that example, but it was on the previous page. Lenz's Law. You can see a question like this, and you might see something like this in the multiple choice with Lenz's Law. And there are some questions in the concept test, which I posted this morning. Again, print them out, 6 slides to a page, and sort of quiz yourself on them. Think about these different scenarios where if I'm moving, say I have a coil of wire and I'm moving a magnet towards the coil of wire, I'm going to get an induced current in this coil of wire that will create a magnetic field that opposes the direction of this magnetic field. Because I'm moving it towards the coil of wire, that's causing the magnetic field here to increase. As I move this here, the magnetic field here increases. Not the induced magnetic field, but the magnetic field due to here. As it gets closer, it gets stronger. Okay, so my induced magnetic field will be opposite because it always sort of wants to keep the status quo. I mean, it doesn't want anything, but physically it will always oppose the change of the magnetic field. It will always try to keep that magnetic field the same, and so that it generates this magnetic field that's opposite the increasing magnetic field. And here it's decreasing magnetic field, and so it's going to be it will be in the opposite direction, trying to keep that magnetic field at what it was before. Okay? We went through a few different scenarios right here. Make sure you follow those and as Lenz's Law is applied in those cases. We did an example here. I think there's a similar example, but you could see something like this where you have to take the derivative of the magnetic field function B with respect to T, how the magnetic field changes with time. Induced electric fields, that's sort of it. Now in this chapter, you need to know your 3 different circuits, your RL, your LC, your LC, your RL, and then your RLC circuits. You have the equations for all 3 of those, so if I ask you calculations, you'll just need to know which values to plug in. But I also want you to know how be able to sketch the charge or current functions for each of those, and then also know how these energies change back and forth. We spent a bit of time on that, talking about how in LC circuits, that's an inductor and a capacitor, how they swap back and forth the energy in the electric field in the capacitor and the magnetic field in the inductor. Okay, so be able to describe that. You'll have 1 or 2 of these circuits similar to ones that we did in class and similar to the ones that are in the homework. We have to calculate the current or the charge at a particular time in these circuits. All right, there's our LC circuits. Again, sort of how it changes the energy. Here's your take home, and I sent this to you yesterday. Take home where I gave you the function. Load that up a little bit so we can see. I sent it to you on Moodle. And it looked like this. I gave you this function. I gave you the second order differential equation, and I gave you the solution for that differential equation along with the angular frequency, that is, what is the value of omega. I just want you to show me that this is the solution, or this is a possible solution to this differential equation. Listen, to do this, you take the first derivative of this and then the second derivative of this, because this is the value for Q, and so you do the second derivative of Q with respect to T, and then you show that that is equal to this whole thing. Now you'll need to plug in the square root of 1 over LC for omega, but you can wait till after you've done that second derivative. So, you know, if you're pretty adept at doing derivatives, it shouldn't be that difficult, but you can have until Wednesday to turn that in if you like, if you need that extra time. But those 15 points then won't be ascribed to your grade until Wednesday afternoon, if you get the full 15 points, which I expect you to. Just do it, you know. Show that those are correct. Show me your steps in that. Show each derivative as you go along. Okay? I made it 15 points. I want y'all to, it sort of bolsters your grade a little bit. It's more than it's really worth. It's really only about a 10-point question. Okay? You're welcome. I want y'all to do well. I need some good grades on this test. All right? LC circuits, be able to calculate the energy or the current at a given time. And same for our damp oscillations in these RLC circuits. Remember, the resistor takes away energy from the circuit. So while you still get that swap back and forth like you do in an LC circuit, you get a swap back and forth that actually declines over time, like in the RL circuits, where you get those exponential decay functions. You're not going to have to deal with the second order differential equation, but you will have to deal with the solution to it. This is on your equation sheet, so make sure you're aware of how to use it. And there are some homework problems dealing with it as well. All right, there's an example we did. You can look at that, deal with it. And no AC electricity and no transformers. Also no phasers, as we saw. You might see them in the homework. I cross those out. Just take a quick look at the homework. All right, this is like one that we did in class where you have to take the derivative of V to find the changing magnetic flux by Faraday's law. I think this is a similar one. So these are good examples of test questions that you might see. They're not going to be identical, but they'll be very, very similar. All right, I might change the shape, I'll change the numbers, of course, but if you can do these and you understand them, then you should be able to do just fine on the test. Magnetic flux, we did that in class. Here's an RL circuit. Be able to find the equilibrium current. I think we actually did part C. How long does it take to reach 1/2 equilibrium current? I think we did a problem almost identical to that in class, actually. If you have trouble with them, the solutions are online, but if you still have trouble, you can shoot me an email over the weekend. I'll check my email, of course, and I'll try to respond adequately. It's sometimes hard to respond over email, but I'll do my best. Here's one about the LC circuits, inductor capacitor circuits. About the energy, how that changes with time, the frequency, the charge at particular times. And then here's an RLC. Oh, actually, no, let's see. Oh, no, so yes, this one's okay. What we have here is we're actually charging up the capacitor, and then we're with a 34-volt battery, and then we're really just dealing with an LC circuit. So this one's still okay as far as tests. likewise, this one's okay. This is our RLC circuit. Be able to calculate the charge or the current in that RLC circuit at given times, or the charge anyway. I think that's it. You know, all the rest of this is AC stuff, so we're not going to see any AC stuff. Only RL, LC, and RLC circuits in this chapter, Faraday's Law. Okay? How are we feeling about the test? Y'all good on the homework? You feel good on the homework? Do you have any particular questions that you want to go over? Take a minute or so, sort of look through your notes, look through the homework. Number 7, on which one? On this page? Okay, so we have an RLC circuit. It has a 7.2 ohm resistor, a 12 Henry inductor, and a 3.2 microfarad capacitor. And it says that the current is initially 0. That means that all of the charge is on the capacitor to start. And so it says that the capacitor has 6.2 microcoulombs. That means it's been charged up with a battery of some voltage. But I go ahead and tell you what is that charge. Now, I might tell you what the battery is, in which case, if I did that, then you would say, well, Q is equal to CV, and then you could figure out what is the charge. So, you know, this was a little under 2 volts that charged this capacitor to give us 6.2 microcoulombs on that. I want to know what is the charge on the capacitor after a certain number of cycles, because remember, this is going to look, the charge on the capacitor, Q, is going to start at 6.2, but then it's going to decrease in this cosine function, and it will also decrease as an exponential function overlaid upon it. So let's look at the equation. Let me pull up the equation sheet. So for an RLC circuit, notice you have the RLC forced oscillator. That's with an AC power supply. So we're only looking at the damped RLC circuit. To write this down, I have Q is equal to Q times e to the minus RT over 2L times cosine of omega prime T plus phi. Now, as far as we're concerned on all of these, this phase angle is going to be 0. So we didn't really talk about phase and how that comes up. It really is only important when you get into AC circuits. So we're just going to sort of leave out the phase here. We'll just say that that phase is 0. So really we're just dealing with omega prime T. And so we want to find out, calculate what is omega prime. And then in order to do that, we have to first find what is omega. That's going to be the square root of 1 over LC. That's the square root of 1 over 12 times 3.2 times 10 to the minus 6. Actually, I'm going to pull up the solution here so I don't have to do all the calculations. Is that okay if I do that? All right. It looks like I did it a little bit differently. I'll just do it here. All right, so 1 over LC is 1 over 12 times 3.2. I get 161. This is in radians per second. Oh, by the way, I didn't tell you all this, but when you're dealing with this in your calculator, anytime you're dealing with this will need to be in radian mode. So as you're going through with your calculator, as you're working through the homework, if you're getting the wrong answer, make sure that you're in the radian mode. And so then I can also find out what is my omega prime. My omega prime is omega squared minus r over 2l squared. And when I find omega prime, that's going to be, I'm just going to pull it up here. It's 161.4. It turns out in this case that the omega prime and the omega were very close to one another. That's often the case, right? That omega prime is really just sort of like a perturbation away from omega. So my omega prime works out to be 161.4. Now my omega prime is related to my frequency by 2 pi. So I want to know, in this case, I want to know the number of oscillations per second. And so I need to calculate my frequency. And so my frequency, which is, 1 over the period, is equal to omega prime over 2 pi. And that will give us the number of seconds per oscillation. So it's going to be 161.4 divided by 2 divided by 3.14. I get 26 seconds. Or excuse me, 26 hertz, which is 26 times per second. And then my period is 1 over the frequency, which is the inverse of that, or 0.04 seconds. So that tells us how many the time for one complete oscillation. And that's basically the end of the problem, because I want to know the number of the charge rather, for 5 oscillations, 10 oscillations, and then for 100 oscillations. So in order to do that, I would come back here and I would plug in times for n equal 5. That's going to be at a time of 0.2 seconds. At n equal 10, that's going to be at a time of 0.4 seconds. I'm just multiplying that times the frequency. At n equal 100, which is going to be at t equal to 4 seconds. If you have a problem like this, by the way, it won't have all these steps. I'll make it shorter so it doesn't take as much time. Okay, you with me so far? Yeah. I know it seems like a lot to throw at you, but as you get familiar with sort of the equations that describe these circuits, it'll be easier when you see it on the test. Just do it for practice over the weekend, and then when you see it on the test, it won't be so overwhelming. All right, so just taking, for example, the n equal 5, if I want to know the charge at that time, I say Q is equal to big Q, which is 6.2 times 10 to the minus 6 coulombs. That's this value, times e to the minus r, which is 7.2, t, which is going to be 0.2 seconds, divided by 2L, that's 2 times 12 henries, times the cosine of omega prime t, that's 161.4 times 0.2. And then that'll give you the answer. I don't know what the answer is right off, but that'll give you the answer for the charge at that particular time. Okay? And then if I want to know for 0.4 seconds, I'll plug in 0.4. For 4 seconds, I'll plug in 4 seconds. Okay, folks? This one's probably not a great example, but I would give you sort of a pared down version of this for the test. How y'all feeling about this? Feeling okay? Or you feel like you have a lot of work to do? Go through the homework. Focus on the homework. Make sure you go through. Look at the old test too. I mean, you'll see that the problems dealing with chapter 6 and 7 are very much like the homework and the examples that we did in class. I mean, that's still a lot, right? There's a lot of homework. There's a lot of examples we did in class, but go through them. Questions? Difficulties? Okay.
What's the difference between, on page 193, you have the RLC circuit, and it asks for the maximum current.
Okay, hold on, let me go to that page. 193?
Yes.
Okay, the maximum current. Yeah, okay, yeah, so this is an LC circuit. We talked about, remember how we're switching back and forth on the previous page, I think. Your question is, what's the difference between the maximum current and the current at 1 second?
Or just like a number 6 in the homework, it asks for, it says what are the A frequency and B current amplitude of the resulting oscillation.
Well, the maximum current is the same as the current amplitude. Does that answer your question? Okay, yeah, that's the same. Okay, folks, I'm seeing a lot of blank stares. So I think that as you go through the homework, you'll be okay. You gonna be okay for Monday? Okay. Are we okay for now? All right, listen, I'll be around this afternoon. I have a meeting at 2, but between now and then, I'm pretty much free. So if y'all want to sit down and talk about particular things, we can do so. But want a good showing on this exam. I'd love to have every exam be perfect. I mean, it's just a lot easier grading and stuff for me. So, okay? I'd love that. That would be awesome. And give y'all a good standing going into the final. If you want to start looking at the final, probably not, but the final will be made up of the 4 exams, just like last semester. I think I've had you all in the previous semester, yeah. It'll be just like the 4 exams, or not just like them. I'll take the 4 exams, change those questions up, but if you can go through our 4 exams and do well in them, you should be okay for the final. People do poorly on finals sometimes, but the average overall is usually at least 5 points higher than it is on the 4 exams. Okay? So encourage you a little bit, but don't be too encouraged by it, because sometimes people do poorly on the finals. All right. Y'all have a good day. I'll see you Monday at 7:15. I don't think you'll need the extra 15 minutes, but some of you might, so I recommend that you come then.